Hi everyone. Today we're going to talk about similar figures and the relationship between their areas and their volumes. So you have already gone over a little bit about the similarity or similar two-dimensional shapes and how their areas are related between one shape and then an area of another shape that is similar to it. But today we're going to take that one step further and we're going to talk about three-dimensional shapes. So if you go to the assignment in Canvas, it should be called something like 9.1.4 volume ratios. And then you follow along. I'm going to be going right through that assignment. But I do think many of you can probably approach this assignment on your own and try it out and see how it goes. So I would suggest if you're interested in that and for a little challenge and trying to learn it right away on your own, go through the assignment and then come back to the video after you've tried it and you want help. If you wanted to stay here right now, that's totally fine, and we'll go through this together. So on the assignment, you're going to see this little rectangular prism right here. Now it kind of looks like a cube, but you know it's not because the dimensions are not all the same. To be a cube, all three of these measurements, the length, width, and height, would all need to be the same number. Here they're not, so it's a rectangular prism. But you'll have two tables down below. And one table discusses the area of the base. So that's sticking to the two-dimension study that we had from Unit 8, where you looked at the similarity of areas of two-dimensional shapes. But the next table is going to deal with volumes of three-dimensional figures. So let's get started here and understand what this table is asking for. So the first column in this table simply says, what is the original area of our base? And that's a pretty straightforward question. You want to look at the prism we have listed, and clearly the base is the highlighted portion in purple, or a bluish purple, and the area is just length times width. So that's going to give us a total of 20. 5 times 4 is 20. But then it's saying, what if we had a similar prism where we scaled every dimension by a factor of this number right here? Well, for this first row, that number is simply 1. And so our new prism will be the length times 1, which is 5 times 1, which is still 5. The width times 1 is still 4. The height times 1 is still 3. So this is kind of our base case to look at what the pattern is as we increase that scale factor. But it's important to have as a base case. So when it says the new area of our base, well, it's saying what is the area of this new prism? And again, it's 5 times 4, which is 20. So the ratio of the area of bases is saying what is the ratio from the area of the base of our first prism to our second prism. And here it's 20 to 20 or 1 to 1. They're the same. And so usually we're going to write it as a fraction, 1 over something, but for 1 to 1, we'll just write it as 1. But this prism I have right here, I did kind of draw with the tools I have in this video platform, but I would suggest as you're going through the assignment on your paper to draw a prism of your own, so then you can label the length, width, and height as you go down, because your numbers are not going to be the same. You're going to have new numbers, so you'll want to have that as a visual representation as you go forward. And just one last brief reminder about what similarity means. Similar means the same shape, but not the same size. So remember, congruent is another term we use, but that means same shape and same size. So really, I know the drawing is off, but you could say that the base of our original prism here is congruent to the base of our new prism because it was a scale factor of 1, so it's 4 and 5 on both. But as soon as we expand that, we times all dimensions by the same number, we're going to have the same shape of a prism, but no longer the same size. So that's what we're studying here. What is the effect of having a scale factor on our dimensions when we look at the area and the volume? So let's jump right to the second part. So the second part, or the second row, excuse me, says we're going to have a linear scale factor of 2. So what that means is we're going to times all these dimensions by 2. So on the bottom, we'll have 5 times 2, which is 10. The width, we're going to have 4 times 2, which is 8. And the height is 3 times 2, which is 6. So what is the original area of the base? Well, that doesn't change. We still have the same prism, and that's going to be 20. But we do now have a new area for the base of our second or our larger prism. So we have, I'll get out of this so we can see it, 10 by 8. So again, it's just length times width for the area of the base. That's going to be 10 times 8, or 80. So when we're asking for the ratio of the area of the bases, we're going to go, what is the ratio from the area of the first base to the second base? And that's 20 to 80. But we want it in a reduced format. So we're going to actually write it as a fraction in reduced form. So if you were to use your calculator, and you were to write 20 divided by 80 or type it in, and then use the fraction number to get the fraction, that would simplify it for you. But I think for some of these, you could do it in your head. And 20 to 80, you probably could do on your own and see that that is just 1/4. It's a little smaller so it fits, but hopefully you can still see that. 20/80 simplify is 1/4. So our ratio of area is 1:4 for a linear scale factor of 2. Let's see what happens when we change that linear scale factor to 3. So for 3, we're going to now take each dimension and times by 3. So we get 15 on the bottom, we get 12 on the side, and 9 on the top. So again, the first column remains the same. It's simply 20, and the new area of the base is for our new base, which is 15 times 12. Use a calculator if you need it, but I would go 15 times 10 is 150, plus 15 times 2 is 30 more, so it's 180 right there. So again, we want to find this ratio of the bases. So we're going to have 20 to 180. But we want to reduce it. So again, use a calculator if you need. But this is going to end up being 1/9. You may start to have a guess in your head of what the pattern is going to be. And I know this is similar to problems you've done before, so you probably know. But let's see number 4, and then we'll know the pattern to go for the general case. So our linear scale factor of 4, we're going to get 5 times 4 is 20, 4 times 4 is 16, and then 3 times 4 is going to be 12. And for these problems in the first table, we don't really need that height. I'm just doing it so we can keep track because we're just doing the area here. So again, 20 for the area of the original base. Second base, 20 times 16. I'd go 16 times 10 is 160, times 2 to get to times 20. So 16 times 20 will be 320. I'm just trying to explain a little bit of how I do the math process in case you want to know some more mental math tricks. But you get 320, which is a ratio of 1/16. So now I want you to think for a second on your own, pause if you need to, and look at the pattern we've developed here. That's what math is. Math is, in a lot of cases, just understanding and looking for patterns. So we want to know for the general case. So we're saying a linear scale factor of r. So if we times it by anything, what's going to happen? Well, this first column, definitely going to stay the same. We're maintaining the same prism for that first column all the way through. But for the new area of the base, what ended up happening? Well, let's look here. For a scale factor of 1, it was 20 times 1 is 20. For a scale factor of 2, it was 20 times 4 is 80. For a scale factor of 3, 20 times 9 is 180. And for a scale factor of 4, 20 times 16 is 320. And so you'll notice each time in this column, we're actually taking 20 times our scale factor squared. And it's going to be the same case, or the same idea for the general case. We'll get 20r squared. And again, similarly, in this ratio of areas of bases, we see that the denominator of this fraction, and really it's a ratio, so it's not exactly a straight fraction, but we can look at it as a fraction. So we have 1/4, 4 is just 2 squared, 9 is 3 squared, 16 is 4 squared. So it's going to be 1/r squared. So that means if I told you we want to have a linear scale factor of 5,000, it's a massive number and it might be hard to test if you're going to really figure the problem out and write all the numbers down. But with this general case right here, you know you would just do 20 times 5,000 squared, which you can plug right into your calculator. And so we're going to do a very similar thing, except we're taking it up a level. We're actually looking at the third dimension, this 3-dimensional prism. So if we're going to change the linear scale factor, if we're going to times each dimension by some number, how is that going to affect our volume? Again, take a chance to pause the video and guess if you want, because I bet you could have a pretty good guess on your own. Don't go through it here. So our original volume, how do we find the volume of this shape? We studied that just recently, just last week. And so what we did is the area of the base times the height. And actually for a rectangular prism, it's fairly straightforward. You can simply go length times width times height. So here we'll have 5 times 4 times 3 gets the total of 60. Now, for this linear scale factor of 1, this prism will be the same. I wrote it last time, but just imagine we have the same numbers. So it's going to be 60 again, and the ratio of volumes is simply 1. That's our base case again. But let's look at what happens when we have an actual scale factor of 2. So again, for our length, we have 10 because it's 5 times 2. Width is going to be 8. And our height is going to be 6. So back down to our table here, our original volume still is 60, but the new volume is going to be length times width times height, which is 10 times 8 times 6. 10 times 8 is 80. 80 times 6 is going to get 480. So what is our ratio of volumes? Well, 60 over 480. If we simplify that down, we're going to get a ratio of 1 over 8, or 1 to 8. All right, let's check out the next one. Because often with patterns, you need to look at the first several cases to really get a sense of what's going on, even if you have a guess. Sometimes you can be wrong based off of 2 cases. So let's look at a scale factor of 3. Our length is 15, our width is 8, and our height is going to be 9. Original volume, again, always the same, 60. But our new volume is going to be 15 times 8 times 9. Again, as these numbers get bigger, you may want to go straight to your calculator. But what is our ratio of volumes? You'll get 1 over 27. So before, our ratio kind of moved a little slowly. We had 1, 1 over 4, 1 over 9, and we're already drastically changing that ratio just by going to 3 for the linear scale factor. Let's look at 4 and see if we can begin to create a conjecture or a guess about what the pattern is. So for our linear scale factor of 4, the bottom's going to be 20, the width is going to be 16, and the height is going to be 12. 60 is our original volume, and our new volume is 20 times 16 times 12. I may tap out here for the sake of time and put in my calculator. 20 times 16 times 12 is 3,840. For our ratio, 60 divided by 3,840, I'm putting my calculator and I'm going to fraction, and I get 1 over 64. Take a second, make a guess on what you think the general case is of R. I'm going to actually write it out this time so that we can get a sense of it, instead of just thinking about it based on the pattern. So if we had a linear scale factor of R, and again, R is just a variable to represent some number. Well, our base, the length of it would be 5 times R. Our width would be 4 times R. Our height would be 3 times R. So our original volume, again, would remain 60, but what do you expect is going to happen for that new volume? Well, we would still take length times width times height. So we would do 5R times 4R times 3R. And what you'll notice is you have those original numbers still in there, 5 times 4 times 3, and then you have 3 separate R's. So we get 5 times 4 times 3 is 60 times R cubed. 60R cubed. Sorry, my bottom of the computer is coming up in that video there, but we have 60R cubed. So you could have done the same thing for the area where you actually looked at 5R times 4R, and again, that's why we got 5 times 4 is 20, R times R is R squared. That's why we got 20R squared. So you can either observe the pattern or plug in that R, because here we had 60 times 1 is 60, 60 times 8 is 480, 60 times 27 is 1080. But I like looking at what's actually happening with that formula of length times width times height. So our ratio here, as you might expect, is going to be 1 divided by R cubed, or 1 to R cubed. So that's how we observe the ratio of volumes. So if you have a linear scale factor, if you say that some shape, the length of one of the bases is twice as long as the length of the other base, you have a linear factor of 1 to 2. Well, the area ratio would be 1 to 4 because it's 2 squared, and the volume ratio would be 1 to 8 because it's 2 cubed. So you can see how that linear scale factor has a greater and greater effect as we look to higher dimensions. And I'll tell you, it'd be the same if you consider the 4th dimension. We're not going to go there, but that's the pattern we can observe. So go ahead and try this out with your own numbers if you haven't already, and then see if you can go to the problems after that and do those on your own. Good luck.